Hello, everyone. This is Daniel Dadush from the Networks and Optimization Group. I want to start by saying that it's been wonderful working and doing research at CWI for the past 6 years, and I'm honored to speak for the 75th anniversary. I'm going to talk to you today about integer and linear programming beyond the worst case. Now, the high-level question I'm interested in this talk is why are simple algorithms so unreasonably effective in practice? Now, we have many instances of this for optimization problems that we solve all the time these days. An example that many of you may be familiar with is the training of neural networks via gradient descent. So here you can imagine that we have the task of building classifiers, say, that can distinguish images of cats and dogs. And we know that we can now do this very effectively if we have a large set of labeled images, and we slowly move the weights of our network iteratively in the direction that minimizes the average classification error over our data set. And if you do this for a long time and use a lot of computational power, you can very often get a very good classifier in this way. The second example is the so-called two-opt heuristic for the traveling salesman problem. This problem is where we want to find the shortest tour that visits every point exactly once, as you see in the picture. And the two-opt heuristic is a famous heuristic where you just pick pairs of connections and swap them in case they make the tour shorter. And if you do this iteratively until you can no longer find an improving swap, you very often get extremely close to the globally minimal tour. So we have these examples of simple algorithms that work unreasonably well for very complicated optimization problems. And from a theoretical standpoint, we would like to be able to explain why. Now, first analytical challenge that shows up almost immediately is that for many of these problems, it's very easy to find examples where the methods perform very poorly. So here you can imagine that in the picture, you're trying to minimize a complicated function. And if you start in the wrong place and use a local greedy scheme like gradient descent, you could easily get stuck in a local minimum that's very far from the global minimum that you might be looking for. However, in many of the applications that we have in mind, this kind of worst case behavior is very rare or rare enough in practice that the algorithms still remain very useful. Now, there's been a long line of disparate works on different algorithms that have studied exactly this question. But it's only recently that they've started to be unified under the umbrella of beyond the worst case analysis of algorithms. And in fact, just last month, the first comprehensive book on the subject, edited by Tim Roughgarden, was just published. Now, the high-level goals in this area are to provide rigorous theoretical models that explain the observed behavior of algorithms in practice, as well as to develop new ways to measure the performance of algorithms that may be more adapted to the applications. Now, there are many motivations for this. The first is obviously that theory should try and keep up with practice. The second is that once you understand these algorithms more deeply, you can often find ways to improve them. And third, which is important to me because I'm a mathematician, the mathematics behind many of these algorithms is very exciting and beautiful. Now, a common approach in this area, which you will see throughout the talk, is to assume something about the input to your algorithm. So you want to maybe assume that your input is well structured, say that there are no bad local minima for your application, or that the input comes from a suitably nice distribution. Now, this kind of approach has been used to analyze algorithms in many different areas, and you see a list below, each of which is in fact a chapter in the book, including one of my own, which is joint with my student, Sophie Halberts, that will be the subject of part of the talk. So for the remainder of the talk, I want to give you two vignettes in optimization. The first is over the simplex method for solving linear programs, and the second is for branch and bound for solving integer programs. Now, both of these methods are used ubiquitously in practice, yet to this day, their behavior remains relatively poorly understood. Now, linear and integer programming, you see the models on the screen, are fundamental optimization models for problems in the area of logistics and operations research. For example, the traveling salesman problem is naturally modeled as an integer program. Now, there are many available commercial solvers for these problems today. And so if you have a problem that you can express in this form, you can expect to be able to find solutions for it with off-the-shelf methods. So what is the simplex method? It's a method for solving linear programs that was invented by George Dantzig in the 1940s when he was working on logistics problems for the Air Force. And let's see what it does on this three-dimensional example. So in green, you see the feasible region of a three-dimensional linear program. And here the goal is to find the feasible point x star, which is as far in the direction of C as possible. So what the simplex method does is it starts at an arbitrary corner point on the boundary of the feasible region, which is also called a vertex. And it looks at the neighbors of the current vertex, and it chooses to move to one which moves further in the direction of C. So in this case, you can move in this direction. And it does this iteratively and builds a path moving from vertex to vertex along the boundary of the feasible region, always in improving direction of C, until it gets to a point where it can no longer make an improving move. And for this problem, it turns out that once you reach this stage, you have in fact found the optimal solution. Now, despite 70 years of tremendous algorithmic progress on the linear programming problem, the simplex method, or at least variants of it, remains the most popular method to solve linear programs in practice. Now, from a theoretical standpoint, this is very surprising because the simplex method is not in general an efficient method. So there are famous examples due to Klee and Minty in the 70s, which shows that for natural rules of how you might choose the next improving vertex, you can actually end up visiting every single vertex in the feasible region, as you see in the picture. And in their examples, the number of vertices was in fact exponential in the dimension, which yields an exponential running time in the worst case for the simplex method. However, simplex runs very well in practice, as has been observed, and trying to explain this theoretically has been a conundrum for a long time. And there have been many different attempts, and perhaps one of the most convincing is the breakthrough work due to Spielman and Ten, who developed a new way to analyze the practical performance of algorithms, which is known as smoothed analysis. So in the context of the simplex method, their key insight is that these worst case examples for simplex are in fact highly fragile. And so if you perturb the coefficients of the instance just a little bit, and you run the simplex method on the perturbed instance, the bad behavior completely disappears. So here you can see, starting from an instance on the left, what would happen if you were to perturb the coefficients by a little bit of random noise. You would tilt the constraints and push them in and out a little bit, but the resulting problem would still be somewhat close to the original one. And their insight was that around any starting instance of a linear program, there are many nearby instances on which the simplex method runs well. Thereby explaining that the bad behavior of the simplex method is somehow a rare event. What was amazing is that they were able to quantify this behavior quite precisely. So the model they chose was to perturb the coefficients of the instance using independent Gaussian entries. They calibrated the size of the entries using standard deviation sigma. And what they were able to show is that as sigma increases, as the amount of noise that you add to the system increases, the behavior, the expected running time of the simplex method, in fact, improves. So as you get farther and farther and farther away from a worst case instance, you can expect to do better and better. And you can see this in the table of running times on the right, where the expected number of steps that the simplex method takes on this distribution of instances is polynomial in the number of variables and constraints, and inverse polynomial in sigma, which makes sense because it should get better as sigma gets larger. Now, the original analysis of Spielmann and Tang was very long and difficult. It was a 90-page paper, and they got a very, very large polynomial. But with subsequent improvements and simplifications due to Verschinen, as well as myself and Sophie Hauberts, we were able to get the running time to be much, much more reasonable and to substantially simplify the analysis. So I want to move on to the integer programming problem, which is the harder of the two problems. In fact, it is an NP-complete problem. And I'm going to restrict my attention to the case where the variables only take values 0 or 1, which you can think of as on or off decisions. Now, the fundamental methodology that essentially is used by all integer programming solvers today, which is known as branch and bound, was invented by Land and Doig in the 1960s. Now, I'm not going to explain this method in detail today. You can find it in any introductory textbook on the subject. But at a high level, it is a clever way of doing exhaustive search over the space of all 0-1 solutions. So the idea is to roughly organize the search space as a tree, as you can see in the picture below, where what is crucially used are so-called linear programming relaxations, where you forget that the variables should be 0 or 1, and you allow them to range in between 0 or 1. And the value of these relaxations at the different nodes of the search tree are crucially used to guide the search. And the complexity of the algorithm, you can think of it as being represented by the size of the tree that you need to build to solve the problem. Now, as with the simplex method, there are examples where branch and bound by itself does terribly. And here's a very simple example due to Jaroslow, which has only one constraint. And it's very easy to see by inspection that the value of this program should be n/2 rounded down, because the value on the left-hand side is always going to be an integer, and if n is odd, you can't get 0.5 on the left-hand side. But the linear programming relaxations will think that the value is n/2 almost all the way down to the tree, and that's where you get the exponential running time from. Nevertheless, given how ubiquitously branch and bound is used in practice, one should expect to be able to find a large and interesting class of examples where branch and bound performs well, or at least isn't totally stupid. Now, rather surprisingly, at least in my opinion, we didn't have a satisfactory or satisfying class of examples until really just this year, where in breakthrough work, Day, Dubé, and Molinaro showed that branch and bound indeed works well for so-called random packing programs. Now, packing integer program, you can think of it as trying to pick a subset of goods to produce subject to, say, manufacturing constraints, which maximize the profit you would get by, say, selling the items. Now, in their model, they chose the coefficients to come uniformly from the interval 0 or 1, and they were able to show that on expectation, the size of the branching tree is in fact polynomial as long as the number of constraints is fixed. So you should think of the number of variables as being much, much larger than the number of constraints, which is very reasonable in practice. Now, admittedly, the exponent they get is exponential in the number of constraints m, which is huge, but this is really the first result of its kind. Now, when I saw this, I got very, very excited. And because I wanted something exciting for my students, Sander, Sophie, and Samar to do during the pandemic, I had them adapt this result to the Gaussian setting, where the coefficients of the instance are chosen from the Gaussian distribution. And we were able to prove the analogous results, though we managed to improve the exponent from being exponential in m to polynomial in m, which we were very happy with. So in conclusion, what you should take from this talk is that the behavior of many of the fundamental algorithms that we use today is still very poorly understood, and that there's a lot of work that's left to be done in this area. And in particular, we really need novel analytical approaches to help us better model the behavior of these algorithms in practice. So that concludes my talk. Thank you very much for listening.